When we hold a finished manufactured part, the matte black surface presents a convincing illusion of a flawless, continuous object. But the physics of injection molding dictate an absolute rule. Every single molded product with a hole in it has a weld line downstream of that hole. When two flow fronts of molten polymer wrap around a geometric void, they must eventually meet and knit back together, leaving a distinct physical scar. For decades, the manufacturing industry has discussed this intersection primarily as a molding problem, a minor cosmetic annoyance that the factory floor is expected to chase away by adjusting melt temperatures or injection speeds. That framing is comfortable, but it is dangerously wrong. Labeling this structural reality a mere blemish tricks engineers into treating a permanent physical compromise as a temporary visual nuisance. This cosmetic mindset has generated a lot of industry folklore. The most common received wisdom is the belief that adding a rough, textured surface to the mold will easily camouflage the seam. Supplier guidance tells a different story. The flow fronts are cooler exactly at the collision point, meaning the resin lacks the heat required to press fully into the mold's textured grooves. Because the texture abruptly changes appearance exactly at the joint, the raised features actually cast microscopic shadows when light strikes the surface at an angle. The factory floor's attempt to hide the seam does not vary the weld line. It actively documents and photographs the failure for the end user to see. To understand the actual penalty of this defect, we have to look past the surface aesthetics and plunge into the microscopic structural reality of the joint. The molding process is violent. Two waves of molten polymer are forced rapidly around an obstruction, crashing together under high pressure, forming an unsettled boundary. To increase the durability of these plastics, engineers mix in reinforcements like glass or carbon fibers. The goal is a specific fiber orientation, forcing these stiff microscopic rods to act like rebar in concrete to bridge internal gaps. But at the weld line, the material betrays the design. Instead of piercing through the newly formed boundary to create a bridge, the microscopic fibers turn and lie parallel along the seam. The refusal of reinforcement fibers to cross the divide leaves the joint internally compromised, creating a microscopic structural cliff edge beneath the surface. When we measure the forces involved, the data proves a massive and highly counterintuitive loss in durability. Standard plastic, like neat polypropylene, retains roughly 90% of its native strength across a weld line. Add 30% carbon fiber, and integrity at the seam plummets to 27%. That 73% reduction leaves the reinforced composite vastly weaker than unfilled plastic. The math is so brutal that material suppliers turn these figures into strict design rules, mandating that engineers treat these weakened seams as severe, distinct load cases when calculating stress. The very act of adding carbon fiber to strengthen a product ironically guarantees a catastrophic localized weakness. If the structural failure is created entirely by the collision of the fluid, what mathematically dictates exactly where that collision occurs? The answer is the gate. This is the precise entry point where molten plastic is first injected into the tool, and it exerts absolute control over the flow path. The placement of this gate, along with every wall thickness and mounting hole, is locked in during quiet tooling reviews months before manufacturing even begins. The physical failure seen on the factory floor is the delayed, inevitable result of a geometric choice made on a computer months earlier. Tweaking injection speeds at the factory is futile. Process adjustments are just trimming a defect whose exact address was already hard-coded during the concept phase. To manage the physics of the material, design teams must rely on advanced mold flow simulations to predict the flow paths long before physical steel is cut for a tool. This simulation visualizes the risk. By intentionally moving the gate in the digital model, designers can shift the flow path, steering the inevitable scar away from areas of high tension and landing it safely in a zone that will experience zero mechanical stress. Eventually, the digital simulation ends, and we finally return to the quiet, hard reality of the physical, completed object. True design means understanding the physical consequences of your geometry. It demands that you see every angle and trace the path of every flaw, long before you build.